Welcome to CS4510. I'm losing track of the lecture. This is 8A. The topic for today is Turing machines. So we're going to talk today basically about a definition, and then we're going to talk about why the definition is a good one. But we'll do that after. So first we just need to know what we're talking about. So recall where we are context-wise in the class. We have currently proven, for example, we started with a model of computation, which was a DFA, and then we showed it was the equivalent to the NFA, and we had something like this, right? Whatever, right? And these were able to do things like A to the N, which is just A star, but we couldn't do things like A to the N, B to the N. So we defined a computational model, observed its limits, it has no memory, it has a constant amount of memory, so it can't do arbitrary things. So we were able to construct such languages, such like A to the N, B to the N, that it could not decide. We took the model, and then we modified it. We constructed a PDA. The PDA, pushed down automata, was really just an NFA plus a stack, right? And what does the PDA look like? You have your input here, and then you have stack here. And it reads through the input in a right read-only manner, and it can push and pop to the stack as it computes, right? And we observed that such devices were able to do things like A to the N, B to the N, but we have a similar pumping argument because they're still quite recursive in nature. So they could not do things like A to the N, B to the N, C to the N, right? In some sense, a PDA is something that can memorize one item at a time. And if tasked to memorize two things or reuse some of its previous memory that's already read from, it's unable to do it, right? This was able to be decided because you push the A's in and you pop the A's out and you make sure those match. Here, you couldn't do this because you push the A's in, you pop the B's out, and then like, well, now you popped it out. By reading it, you've sort of thrown it into the ether, it's lost to time. So we need some other like data structure or something that we can adjoin to a simple automaton that can keep track of stuff in not necessarily a forgetful way. So of all the data structures you know, what's another one?
Array or list?
Yeah, so like what if we don't, every time we want to read something, what if we don't have to pop it and forget about it? What if we just keep it there? So that's all a Turing machine is. It's a DFA plus, instead of an array, we'll call it a tape, as we'll see. So that's all really a Turing machine is it doesn't have to forget in order to do it. And were I to draw a picture of a Turing machine for you, it would look like this. Something like this. And then there is this, what's called the tape head, which is basically a giant paperclip. And then there is something called the tape. And the tape is just this one-way infinite, something like this, right? It's just this one-way infinite scroll in some sense that are demarcated according to some cells. Something like that. And each of these contains a symbol that it can read and write from. A, B, A, and let's say blank, 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 right? So the way the Turing machine is initialized is not in two separate devices like the PDA where it's got an input and a stack. Here, they're combined into a single tape. The tape is a sequence of symbols such that the input is initialized onto the tape in the leftmost cells. So here, for example, the input to this machine would be ABA. Now, the rest of the input is there, but it's allocated as blanks. It's just a bunch of blank symbols there. And the way the Turing machine computes is it can read and write to the tape, and it can move a single cell left or a single cell right. So what it can do is sort of like loop over the tape in some patterns, reading and writing symbols conditionally. That's all the Turing machine really is. And we're going to give a formal definition of the Turing machine in a second, but this is basically all it does. And notice because the way the tape is not like lossy in any way, we can just combine these two different things. Instead of having two separate things, we just say, just put the input on the structure for it. So we don't have to deal with a complicated transition function in this way. Questions on that so far? Yeah, let's give the formal definition. So of course you know it's going to be a tuple of stuff. The tuple specifically is going to be Q, sigma, gamma, delta, and then Q0, QA, and then QR, which are designated states. And the way these are going to work is Q is going to be our finite set of states again, like always, Q0 to some QK. But then there's also these QA and QR, which we'll say what they are in a second. we have sigma, which is our finite non-empty alphabet, and it's the input alphabet, and traditionally, of course, this is going to be like AB or 0, 1. We now have gamma. Before gamma was a stack alphabet, here gamma is the tape alphabet. And it has some extra conditions on it because we're combining these two things into one. First off, it is the case that the blank is an element of gamma. The blank is a special symbol that means nothing is there yet. But by being part of the tape alphabet, the machine technically can read and write it. So it's a blank, it's an unallocated thing, and the way we say the cell is empty is we have a special character that says this is the blank, right? The second thing is that the blank is never an element of sigma. So the input will contain A's and B's, or zeros and ones, or A, B's and C's, but the input will never contain the blank symbol. This is the difference between the input and the tape. The tape will contain this extra symbol that the input will not. And finally, we must require that the input alphabet be, in fact, a strict subset of the tape alphabet. So while in the PDA definition you could have the input be A's and B's and the stacks be C's and D's, and then you could, as long as you did everything appropriately, that was technically fine. Here, that's not the case. The input must be a strict subset of, the input alphabet must be a strict subset of the tape alphabet. And conventionally, the tape alphabet will usually just be the input alphabet with the blank, right? So by convention, most of the time, this will be true, right? If you just wanted to think of it that way, that would be the case. Now, when that won't be the case is when we want perhaps more useful symbols in the tape alphabet to do something interesting, right? Let's talk about what the transition function ought to look like. What was the transition function for a DFA? This is the DFA, right? The transition function for the DFA was like, I'll just do it here, right? For the DFA, the transition function looked like, we took a single symbol, a single state, a single symbol, and we moved to a single new state, right? For an NFA, it was, we moved from a single state, optionally read a symbol by having epsilon transitions, and then moved to a set of states by the power set, right? The PDA was also non-deterministic, and it was, you take a single symbol, you take a symbol off the input optionally, you take a symbol, you pop a symbol off the stack optionally, and you move to a new state, and you pushed a symbol optionally, and you did that non-deterministically. So this would be the power set, right? So those are the domain and codomain of those previous automatons' transition functions. But what's the Turing machine's transition function, right? So first off, it's deterministic. Why? What's the difference between a non-deterministic Turing machine and a deterministic one? Is a very old and in some sense unsolved question. So our definition though is going to be deterministic. Okay, so we know that we want to read and write symbols to the tape alphabet. And we want to do so upon transitioning between states. So what we'll do is we'll say, if we're at some current state, what we're going to do is read a symbol off the tape. Then we want to move to a new state. We want to write a new symbol. And then we want to move the tape head left or right. So the way we do this is we put L, R as special symbols here. And those special symbols are going to say, okay, read, then write, move, right? So what you can do is you read a symbol, and then you're going to write a symbol, and then move the tape head left or right. So what that means is this little paper clip moves left or moves right, one cell, right? Right, and the way you would denote this with a transition would be of the form something like this, right? So read an A, write a B, and then move left, for example. That would be the way you denote it when we do state diagrams. The final piece is Q0 is the start state. What do you think QA and QR are?
Accept, reject.
Yeah, QA and QR are going to be designated accept reject states. So here's another power we're giving the Turing machine over the other automatons, which is not particularly important. The PDA must accept after reading all the input. So it must read all the input and then take some epsilon transitions. And how many epsilon transitions it can take, it is stuck there, right? So the PDA has to halt after reading the entire input. The Turing, and so it does the DFA and so on, right? The Turing machine instead has two designated states. Instead of half the states being accepting states and half the states being rejecting states, here there's just two special states, right? So the way you should think of it is like if you transition to QA, it's as if you're calling an instruction to say accept. Like it's designated when you want to accept. You can't like accidentally accept. You can't accidentally reject. It has to be on purpose, right? You transition to that state. Now that means you don't have to finish reading the input. You can just give up halfway through and say, oh, okay, cool. Let's say you wanted a Turing machine to check if the first letter was an A. What you do is read the A, okay, cool. Transition to the accept state. Don't even have to read the rest of the input. Something like this, right? So this is a difference between the Turing machine and then the PDA and other things like this. And this will end up causing, I won't say cause more issues, but it is distinctive enough that it makes the Turing machine vastly more interesting than the push-down automaton. Right? Questions? And this is the formal definition. These are all the parts of the tuple. Questions on this so far? Right. The rest of today's, the first half at least, will be spent on programming such machines and describing them. So we want to describe instantaneous snapshots of the machine, right? We want to consider how computation is a process. It goes through a sequence of steps. So we want to be able to illustrate those steps. So a configuration is an instantaneous snapshot of a machine at a specific moment in time. And when you play around with VMware or the open source equivalents or whatever, right? You can click snapshot, and then you can go and restore such a snapshot later. And it stores basically all the information that's, even for like a Game Boy emulator or whatever, you can even the emulator will have like a save function independent of the game save function because it just copies everything down for you. But what is it really copying? It's copying, for example, all the RAM, it's copying the location of the mouse pointer, it's copying all the registers, every single thing of that instant is saved to some encoding. And then that is restored in some non-trivial way. So what is a snapshot of the machine? What is all the information needed to encode a moment in time of a Turing machine? So first off, it's going to be contents of the tape. Okay, fine. What else is it going to be? It's going to need, what else? Yeah.
States.
Yes. So not only the state, but the current state. It'll need the code of the machine as well, but let's just suppose we have that, and we're just looking for the other information besides the program description. So we already have the program description, we have the contents of the tape, which is analogous to RAM, and we have the current state, right? So it's some QI or something, right? Well, there's one more piece of information we technically need. Yeah.
If it's been accepted or not?
We can determine that from the current state because if it is QA, we know it's accepted. And QA and QR also have like no outgoing anything from them. They're just like there, dead stop, you know?
Gotcha.
Like nothing comes out of that, right?
You need a location of the head.
Right? Yeah, we need to figure out where that head is. Location of tape head. And there's a few ways you can actually encode all this. You could encode the location of the tape as a natural number. You could encode the state as a natural number. You could encode the contents of a tape as a string. But if we were to consider a machine an instance, let's say we had something like this. A, B, C, D. And let's say there's some things to the left and some things to the right. And let's say that the current state is QI and it's pointing at C. Okay? So here's the contents of the tape is, let's say, A, B, C, D. The current location is pointing to C, and that this current state is QI. Now we want a way to encode all this in something concisely. Now this is not science, it's just sort of a bit of engineering. tell you the data structure of the configuration is just going to be a string. And there's a cheeky hack we can use to encode all this information at the same time. The way we'll do this, the configuration representing this is going to be a string over the input, the tape alphabet symbols, as well as specific symbols for the states. So this would be represented by the configuration A, B, Q, I, C, D. Right? Now, basically, this is 3D, this is 2D. So we just have to make a convention. And what that means is, when we see this QI, what's immediately to the right of it is what the tape head is pointing at. Okay? That's immediately what comes next. So suppose we had a transition of the form read C, write C prime, let's say, and then let's say move right. Okay? And as we do so, let's say we're going from QI to some, let's say, QJ. What would the next configuration be? Well, let's break it down. What would the next state be? It'd be QJ, right? The contents of the tape would look like what?
A, B, C, D.
Almost. Let's suppose we executed this transition. What changes?
C is moved.
C gets overwritten by a C prime.
Okay.
Yeah, this is just the convention. So it happens, you read C, then you write C prime, and then you move right. Right? So, and this transition can only be taken if the current head was reading a C. Right? If it was reading a B, there'd be maybe some other transition. Right? So we know that the tape contents looks like this. Now, but where is the tape head now pointing?
At D.
Yes. So what the next configuration is going to look like is going to be what?
A, B, C, Q, I, D. Or sorry, Q prime.
Yeah, C prime, Q, J, D. Yeah, I think, yeah. The first time, it's okay. Right. So what we say is that by convention, one configuration can yield another. So we can say, for example, C0 will yield C1. And we use this symbol here to mean yields. Right? Suppose we wanted to move left instead. Suppose we were at this specific configuration of a machine, and we had C write C prime, but instead we moved left, right? And we go from QI to QJ. We would go from this to what? What would our next configuration be? Without me writing the picture of this snapshot of the machine, what would it be?
A, B, Q, J, C prime.
So we know it's a C prime here, we know it's a D, and we know there's a Q, we know it's QJ.
Sorry, I was going from the bottom one.
Yeah. So let's go from here. Let's go from here. This is a convention and this tricks everyone up the first time.
Is it A, Q, I?
It's going to be QJB. Now, why does that make sense? I mean, it looks like we we wrote the C over here, but now we're like 2 away from it. So what's going on? Basically, this is 3D, this is 2D, and this is 1D. So we have to like make some convention. What's immediately to the right of the letter is what's being pointed at. So if we read the C and then wrote a C prime and then moved left, this QI is going to go in front of the B. So now it's QJB, C prime, right? So we say this configuration yields this configuration. And these are just 2 strings, right? So, yes?
Do you always have to move?
Yes. Now, in practice, does it really matter? Like, the transition function, by the way, there are many variants of Turing machines with in every book has a slightly different definition. That's not true for DFAs. Every book has the same definition of a DFA. But every book has a slightly different definition of a Turing machine. And why? It turns out they're all the same. So let's suppose you wanted to read or write or move instead of read, then write, then move. Does it really matter? Or what if you had a Turing machine with a stay operation? Like let's say you didn't have to move. It turns out that this definition is the simplest one to work with when we do proofs of things. Like, it's going to make the proof so much simpler. For example, you could emulate a stay operation by reading nothing, writing that same symbol back, and then just moving left, and then moving right back. Right? Read, write, move, right, and then move left. So like that would just be stay, right? So you can do such things, and it doesn't really matter. But this allows you to assume that the Turing machine must move, which ends up simplifying some proofs and so on. So we'll have to see that later. But just know that this is the formal definition. Why it's a good definition will in some sense be the remainder of the entire course. Questions on configurations and so on, right? When is the Turing, we say, what is the definition of accepting? For example, we say a DFA accepts a word if there is like a path in the graph following that word that leads you to an accept state. So how do we define the accepting of a Turing machine? We say Turing machine, let's say M accepts if there is a sequence of configuration C0 to CK such that, we'll say, even further, we'll say M accepts some specific word W, which is W1 to WN, where those are symbols of the input alphabet. If there exists configuration C0 to CK such that C0 is the initial configuration. What's the initial configuration of the Turing machine for any input? Let's say the input's W1 to WN. What's the initial configuration?
Q0, W1, WN, and then a bunch of lines.
Yeah. Now the blanks in a configuration you're allowed to write, but it's like leading zeros. So you only need to write them if you necessarily may need them, but you don't have to write them. So this is technically still valid. But in terms of aesthetics, we'll just kind of, we know they're there, and we'll only write them if we need to read them, for example. Okay. For all I, which is sufficient between 0 and k minus 1, we say C of I yields C of I plus 1, right? So by yielding, this is according to the transition function of the Turing machine, where these are all strings. And then we say CK is accepting. Now what is the accepting, how do we determine if a configuration is accepting?
If it's in an accept state.
Yeah, and the way you do that is this symbol QA, literally a character in that configuration. So this is the formal definition of when a Turing machine accepts, right? Right, questions on this one? So let's give some, now we've talked intimately about the definition, let's talk about actually writing a program, right? So, of course we're gonna, because we're generalizing the automatons, we're gonna pick a program that we have not been able to give a PDA for. The one specifically we're gonna give a Turing machine for is going to be, let's say W hash W, so that W is in sigma star. By the way, when we did the PDA, we were able to do WWR, right? Because the stack comes out in reverse. But how are we able to determine the midpoint of this? Does anyone remember?
With the PDA?
Yeah.
When the stack was empty?
That was at the end. But how did we know to stop pushing W and start popping WR? Yeah. Yeah.
We don't. We just non-deterministically do it.
Yes, we non-deterministically guess when to stop counting there and start counting there, right? Turing machine, deterministic. So we can't non-deterministically guess the midpoint. Turns out it doesn't really matter. Like, you can still determine the midpoint in a Turing machine because it doesn't have to pop and push and so on. But we're gonna just help the machine here by doing W hash W instead of without the hash, because the hash is just going to help us keep track of where the middle is. So if we ever read the hash, we know we're at the midpoint, right? And suppose I wanted to create a state diagram for such a machine. Before we do so, you always have to be influenced by your own intuition when it comes to writing code. So before we get to the Turing machine, give me code to write such a program. Like at a high level, how would you determine if a string is of this form? You want to accept or reject if a string looks like this? Yeah.
A bunch of if statements.
Sure, but what would those be? What would these statements be?
For a specific string?
Yeah, let's say we have an input like A, B, A, hash, A, B, A. How would you determine if that's correct?
A bunch of nested if statements. If A is equal to A.
What if the input is a billion length? It needs to be independent of, the size of the program must be finite, but the input could be long.
You can loop over it.
Okay, so describe the loop process.
You There'd have to be some correspondence with like the position in the input
Okay.
to where you check, to the states, I guess, where you check.
Right, so the Turing machine does not have a lot of memory ability. It can't say split the string, put these separately, malloc and free, and none of that. So it can just like loop left and right. So in a very primitive way, give me a really bad algorithm to determine if this is of this form.
Push to the stack.
We don't have stack yet.
Oh,
But you have a tape, so you can read and write to the tape. And let's say this is already on the tape for us, right? So now you have a tape head that is allowed to iterate over it, and it begins here, right? So you have that little thing that's allowed to loop over this input, and it can read and write. It's allowed to use more tape because eventually there's some blanks here, right? But if it needs more, it can move over there and write something down if it needs to keep track of it. But we don't necessarily need that for this. Yeah.
I have an idea. So
Okay.
you check each character, right? That means you need to, go from left to right, knowing where you've been, right? So
Okay.
you maybe do this, right? I see an A, right? I remember that it's an A, write something to there so that I know that I've seen that, right?
So let's just mark it.
Yeah.
Okay.
Go over to next to the hash, right? Right. See the first letter that is not a hash, right? Check whether it's the same as I remember and put a hash there,
Yeah.
right? And I just keep doing it until the left pointer is the hash now. I don't know whether this is the best way.
Hey, we need anyway. We don't need efficiency. We just need possibility. So what's going to happen is the tape head, unfortunately, there's no jump instruction. It can't just say, in an array, you can say, read me the middle character, n over 2. It'll do it for you, right? You could say, if the array is length n, you can say a of len a over 2, right? That works. And it'll just return you the middle character. That doesn't work here. You can only loop left and loop right. So unfortunately, the Turing machine can't just jump here. It has to go click, 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 click. So you need to know when to stop, right? So what's going to happen is, at a high level, you're going to read the symbol. So let's kind of like make pseudocode. Read the symbol and remember it. Remember? Remember. Okay? Move right to next unmarked. If equal, reset. That's basically what's going to happen. You're repeatedly going to check this A against this A. You're going to reset here, check this B against this B, reset, check this A against this A, reset, check this A against this A, and so on. Now, when do you stop?
When you reset, you see the hash.
Yeah. This is not sufficient to implement the machine, but it's enough to get us started. And as we fill out the transitions of this actual machine, we'll be able to answer more questions by looking at it. This is totally off the wall before we even actually have the state diagram. Suppose we measure the runtime. Now, this is not a class about runtime. That's a much later question. How many steps does a machine take? If we consider click, 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 all those as steps, how many steps does such a machine take to correctly decide a word? If the word is of length n, W is of length n.
It'll be n squared.
It's n squared, yeah. N squared, n squared, n squared, n squared, n squared. Okay, so this is not relevant to us yet. We'll talk about this later. This takes O of n squared. There's some constant stuff, right? Can you do it faster than that?
Using only Turing machine operations?
Yeah. Yeah, that's the trick question. Can you do it faster than this on an actual computer? Yeah, it's like linear time. You just say A of I equals A of n over 2 plus I, right? could do something like that, and that would loop through in linear time, right? So linear time, you could determine this easily. Can you do it in a Turing machine faster than n squared? This is difficult to prove, but you can do it, and the answer is no. So in some sense, the worst solution is actually the best one. We don't know that though. We're just here implementing it. But I want you to realize the Turing machine, at least when it comes to speed, definitely slower. But we're not concerned with speed, we're concerned with power. So, let me see. Power is good enough. So it turns out the fact that it can decide this at all is good enough for us. So let's implement the state diagram of such a machine. So we're gonna have some start state here, Q0, okay? Now, how can we remember? How do we remember the symbol red? There's two ways to do it. There's a good way and a bad way. Actually, when you're writing high-level code, there's two ways to do it. The Turing machine only has access to one of those ways.
Go to 2 separate states.
Yeah. So analogously in code, you could do like if A, then you have some code here, elif B, and you have some other code here. That, if you do it that way, you don't have to actually save a variable whether or not, so the first way is to just save a variable. And the variable will tell you what the letter is. But the Turing machine would have to like write it down over here, and then if it needs to remember it, it'd have to go over here and read it, and then go back again, so that's kind of complicated, so we don't really allow it to do that. I mean, we do, but it's not gonna help us. Instead, we just have that information stored in some sense in the control flow. Because you know if you're in here, you know you saw an A, and then you know if you're in here, you know you saw a B. So you don't need to remember it, you can just assume it's a B anytime you're in here, and assume it's an A anytime you're in here. So what's what we're gonna do? Where if we see an A, we're gonna write, let's say, an X, and move, let's say, right. And if we see a B, we're gonna write, let's say, an X, and move right. Right. Let's only consider the above branch because these are gonna be symmetrical in some sense. What are we gonna do after we read an A and write an X? So we've just marked this A. What do we wanna do?
Check to see if it's an A on the other side.
Yeah, so what we need to do is chug our way over here and find this A. So we need to skip past a bunch of stuff. So first we need to skip, if we're at the last unmarked symbol, what we need to do is skip a bunch of, if we read an A, we're gonna write an A and move right, and if we see a B, we're gonna write a B and move right, okay? Now we should see one hash. So, if you see the hash, just step over it and keep going right. And we're gonna, if we see any unmarked symbols, we need to just step over them. Okay. Now what should we stop doing this loop? Yeah.
When we see the A.
Yeah. So what we do is we need to make sure it's an A though and not a B. So what we'll do is we say if we see an A, we'll mark it now with an X. And then we'll move not right anymore, but we're gonna move left. Although the distinction is not, you could write a worse Turing machine that moves left and then right and then tries to move back left or something, right? Okay, we're at some state here now. Now we need a reset routine. So we've now marked this, let's say we read this A, we've moved over here, we marked this A. We need now to move back past all the marked. We need to move past all the hash, move past all the blanks until we find the next unmarked. So we would need to reset ourselves. Let's say we marked this A. So we marked this A, we chugged past these unmarked, chugged past this hash, chugged past these marked this A. So now we need to chug past these marked, chug past the hash, chug past the unmarked, and then somehow land on the next unmarked, right? So let's do that in order. How are we gonna chug past the marked, read the X, write the X, and then move left? So that's, you can imagine that moves. Now we need to see we see the hash. So let's just go to a new state. If we read the hash, let me make this longer. If we read the hash, just step over it, write the hash back, and move left. So the Turing machine does not have a do not disturb operation. It must read and it must write. But you can pretend you're not touching it by reading the symbol and writing the same symbol back, right? So we're at some middle state here. Now, if we've moved past all these x's, we've moved past this hash, we now need to move past the unmarked. So we'll just do that again with a self loop. If we see an A, I'm trying to think how to do this space-wise. If we see an A, write an A and move left. If we see a B, write a B and move left. Okay? Now what should we do? Yeah.
Once you see the first marked, you're gonna have to rewrite it as the marked and then move right.
Correct. We're gonna have to move right. So we wanna make sure we're in Q0. We see the mark, we're gonna write the mark, but now it's important, we moved left through this whole branch here, right? We need to move right. So we're going like this way, we see the mark. Oh, good, stop there. Write the mark back, but then we're gonna move right. So by the time we enter Q0, because we're right of the mark, we know we're at the next unmarked. Done. Okay. Now, what if we saw a B at the beginning? Just redo everything. Here, instead, though, we're going to make sure that we see a B and write an X and move left. And then this routine that resets ourselves is the same for both. Now, there's a problem with this machine, technically. What's the problem? Actually, there's two problems. What's the problem first?
It doesn't enter reject or accept state.
Yeah, we need to enter the accept state. So when should we accept?
If we get back to Q0 and the first, in the current input is a hash.
Yes. So if we're at Q0 and we see a hash, read the hash, write the hash back, what should we move? So there's a small bug, there's two bugs here. First off, what if we have an input of the form where the first is not equivalent to the second, but it's a prefix? So if we had something that looks like AB hash ABC, right? What's going to happen is mark, 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 mark. We're going to be pointing here, right? But we haven't finished marking the rest of the second W, so this is a problem here. What should we do? Yeah.
We should loop through the right side and confirm all the inputs are hash or X.
Yeah. So we're going to move right, and then we're going to, if we see an X, write the X, and then move right. And when do we accept?
When we reach a blank state.
Yeah. So if we see the blank, at this point it doesn't really matter if we write anything there because we have confirmed the input. So if we saw a blank, then we're good. So what we do have to do, read, write, move. So let's just say we write the blank back, and then let's just say we move left to right. It doesn't really matter at this point. Let's move right. Okay, done. So now we accept. Okay, fine. We solved the first problem. This is the if we saw an A, reset. If we saw a B, reset. And then if we're done, we go here. Sorry, one second. There's a second problem. What's the second problem?
Doesn't reject.
Yeah. When should we reject?
At the state before QA, if we see an A or a B after all the X's.
Okay, yeah, definitely there. If we see an A or B out going from here, we should definitely reject. When else should we reject? That's the only time. Yeah.
If the letters aren't matching.
So if we were here, we see an A, we mark it. So if we saw a B, we should reject. And here, if we saw an A, we should reject. Where else should we reject? The answer is everywhere else. So like, there is no implicit reject in the definition of the formal Turing machine, But if we pretend there is, it makes the diagrams much simpler. So let's just pretend that we have implicit reject, okay? Every single possible pair of reads, writes, and moves should be defined. So here, if we saw a blank at the beginning, we should reject. Why should we reject? Why is the empty string? So if the input to the machine is the empty string, then the tape will look like blank, 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 blank. So if we see a blank at Q0, we know the input is the empty string. Why should we reject the empty string? Yeah.
Because it's not 2 words, it's only one.
Yeah. I guess in this specific scenario, it doesn't contain the hash, right? So it should reject. At the very least, the smallest string here is just the hash, right? And similarly, so like the transition function must be defined for every possible read state pair. You write something and then you move, always, and then you change state. So let's just throw all that into the reject state, and let's pretend we have that, and there'd be a big... Right? Pretend I did all that, that's all there. It's okay to assume we have implicit reject, it makes the diagram simpler. Questions? Diagram. Now, okay, this is the decision version of a Turing machine. A decision machine is tasked, like all our previous machines, the decision machines are tasked with saying yes or no. But they are not the only kinds of machines that we have. So the Turing machine is also interesting because it doesn't need to simply say yes or no. We're allowed to use the Turing machine as we would a calculator. In the sense that we also have a distinct output that we can look at and say, that's cool, you know. This definition that I'm now erasing is the decision definition. But we can modify the definition to compute a function. So we say f from sigma star to sigma star is computable or Turing computable if there exists a Turing machine which halts on all inputs. It begins with W on the tape, halts only with F of W on the tape. So what this definition of a Turing machine is it's a computing machine and it's not a decision machine. The decision machine has distinct states QA and QR that it accepts or it rejects. The computing machine just has a single state, let's say QH, and it just like stops when it enters QH. And it doesn't stop until it enters QH. And the Turing machine here is not tasked with taking an input and saying yes and no, right? It's not tasked with taking a word W and transforming it, taking a word W hash W and outputting a yes or a no. It's tasked with computing some specific function. So let's do, and these end up being simpler because even though it sounds more complicated, the diagrams become much simpler. So suppose we're trying to compute the function f that is bit flips. So suppose we have a binary string and we're trying to flip the bits of it. Give me a Turing machine that does this. So obviously we need a Q0. Yeah.
If you see a 0, then you write a 1.
And then you
Move to the right.
Okay. What else?
And if you see a 1, you write a 0, and you still move to the right.
Okay. When do you stop?
When you see an empty,
What do you do?
write the empty, move either way.
Yeah, doesn't matter. To make it harder, let's just say you move left. Okay? And then you're just going to go to some QH. There's no notion of accepting or rejecting. It doesn't matter. But notice this machine will begin with W on the tape and flip the bits of it, right? So how should this look? Let's just write a sequence of configurations to confirm that this is what's going to happen. So let's suppose we initialize the configuration at Q0101, right? We're gonna read the 1, write a 0, and then move to the right. So what that's gonna look like is we're gonna read this 1, write a 0, and move to the right. So it's gonna be 0, Q001. That's the next configuration, right? 0, we're gonna read this 1, read the 0 and write a 1 and move right. So it's gonna be 1, Q01. Then we're at this 1, we're gonna read the 1, write a 0 and move to the right. 1, 0, 1, 0, Q0, and then we have a blank here, right? The blanks are always there. You can bring them in as necessary. You can say, you know, yeah. Now what are we gonna do? We see a blank. We're not gonna disturb it. We're gonna write the blank back, and then we're gonna move to the right. Excuse me, we're gonna move to the left, just because that's what we did to make it harder. So it's gonna be, we're gonna be pointing then at this 0. We're gonna read this blank, write this blank back, and then point at this 0. So it's gonna be 0, 1, QH0 blank. And these are the sequence of configurations, and then now we've stopped. So what this computable function does is it takes 101 and it outputs 010, right? So this is a machine that flips bits, right? By the way, Turing machines do not have to halt. Give me a machine that's, a computing machine in fact, that's stuck in an infinite loop. Yeah.
The same thing, but instead of when you see an empty space, you go to a holding state. You just go back, if that makes sense.
Okay, there's a few. So you want to flip bits again. And then what?
So it keeps flipping bits until it's flipped them all, and then it goes back left and starts flipping them again. So
if we see a blank, write the blank, and then move left, and then
same thing as the left state, but instead of moving right, you move left.
and then when do we, here's the problem.
Is there no way to know?
Well, there is kind of a way to know, but difficult. How do you know when you're at the end? By the way, we didn't address this, but conventionally, what happens if you're at the first cell, the 0th cell? You try to move left, what should happen? What should happen versus what does happen?
Should happen? Should break?
Yeah, so it depends on which book you read. It's kind of the answer. What happens in our definition, because we only want to halt when we say we halt, what will allow to happen is that some books say that you stop, that the machine halts. It just must enter a halting state. And you can avoid any programming use of reading this symbol. So what you can do is either at the beginning write a symbol there, like we had a stack canary, and if you ever read it, something you can know this. You can do a similar tape canary. Forget that. What you can do is just program avoiding to use that. What we conventionally say happens is that if you read this, you read the symbol, you write the symbol, but then you don't actually move. You just are stuck back at the same spot. So you physically do not move, but you do read and write, and that's just convention, and that's going to make our proof simpler. But that's just what we assume. So let's not say that we read the bits, write the bits, and move left. Yes.
Instead of going to a halt state when you see a blank, you just keep moving right.
Yeah, that would be simpler. So we could say, read a blank, write the blank, move right. Okay? It's going to read the blank, write the blank, move right. It's going to move the right, it's going to move right. So it's going to flip the bits, and then it's going to move off into the ether. It's going to forever go that way and just like, it's never going to stop. It's just going to keep reading the blanks and writing the blanks forever. So the machine doesn't have to halt, necessarily. PDAs must halt. Even a poorly programmed PDA must eventually terminate because in order to accept, it must exhaust the input. Implicit rejection is all throughout the machine, and it takes only some number of epsilons after it's finished reading the input. So it can never get stuck in an infinite loop. But the Turing machine can, unfortunately. This is both a limitation and a power, as we'll see. Let's do one more computable function. So like, Turing machines are actually capable of calculator math. Let's compute the successor function. So the successor function is S of n is equal to n plus 1, right? It's the function that computes the next number given the previous number. That's succession. So This is in some sense the function that inductively defines the natural numbers. We can give a computable function that takes on input a unary string of 1 to the n and outputs a unary string of 1 to the n plus 1. Give me such a machine to do the successor function in unary.
You would leave all of the ones alone and then make the next blank a 1.
So, describe it to me.
Oh gosh. You see a 1, you write a 1, and you move right
Correct? Until what?
until you see a blank in which you write a 1 and move right.
Yeah, doesn't particularly matter there, and then you just stop. Okay, that's it. I mean, that's still a machine. Now, suppose you wanted to do it in binary. How would you do it in binary? How do you do an add one operation in binary? There's a few parts.
You go all the way to the right.
Okay, first step, go all the way to the right, because the input is in that form, where the small is at the end, as the right end, right? So first, we need to go all the way to the right. How can we do so? Let's break this up into pieces. Every time you design a Turing machine, things are split into subroutines. And then those subroutines are then computed in a certain way, right? So you're gonna be here, how do you move to the right?
Just read. If you read a 1, you write a 1. If you read a 0, you write a 0. And then you go.
You move right, right?
You move right.
Yeah.
And then once you see a empty string, you
Right, yeah.
read it. You write the empty string, and you move left. So now you're pointing at the rightmost.
Correct.
digit.
Now you're focused on the next thing, which is, after you complete that part of the Turing machine, you are now at the leftmost, the rightmost character, right?
And then now there's two options. It's either a 0 or a 1. If it's a 0, that's easy. You just change it to a 1 and you're done. If it's a 1, that means that you have to start carrying over.
Let's say we move right here, okay?
If it's a 1, you have to start carrying over terms.
Okay.
So you would move to the left and
If you see a 1, you write what?
0,
Okay.
and you move left.
Yeah.
What if you overflow?
Let's just assume that we don't have to deal with that because it's complicated. What you should actually do is assume your input does not begin with a 0, right? This does not handle this case, right? But let's suppose that we have a leading 0 there for us, okay? Let's just make that the input, okay? So first we're gonna move over here to this symbol. We're gonna read the blank, okay, well, let's go 1 back. So we go here. Write a 1, we're gonna change it to a 0. See a 1, change it to a 0. See a 1, change it to a 0. See a 0, change it to 1, right? That's basically, this is just a carry operation in some sense. In binary, it's just like, oh, I see a 1, it's now a 0, and then I'm gonna make sure the next one, and the next one, and the next one. It's gonna domino all the way up. And that's all the machine is, right? Okay, now this assumes that the input has enough leading 0s. Again, if we need the next digit, what we really should do is begin checking that it's all 1s, and if it is all 1s, then we shift over, and then we write the correct string. It doesn't, who cares? You know, let's just, in terms of education, I think this is good enough to understand what's going on. And I could leave it to you to do the 7-state version that would handle that, right? Questions on this one? Okay. Let's do, suppose we wanted the unary addition function. So we took in, let's say, 1 to the A hash 1 to the B, and we outputted 1 to the A plus B, okay? Now, computable functions, it doesn't matter if they take on multiple inputs or one input. Because if you had something like this, where the function took multiple parameters, it doesn't really matter. Just encode them with this hash character, and then they're all in the tape in some way, right? How can we give me a Turing machine that takes on input 2 unary strings and outputs a single unary string? That's the sum of the two.
Could you just delete the hash?
Okay, we delete the hash, but then there's gonna be A's, a blank, and then B's. We want one large block of ones though, yes.
When you see the hash, you,
So first off, what should we do? Let's begin.
you want to write the one on the right. So you see the hash, you move right one, read, write the hash, move back left.
It's gonna be simpler. I think that would work, but there's a simpler thing we could do. Yeah.
You get to the hash, and then you just use the 4-state Turing machine that you can use to just left shift, I think. Basically,
It's simpler than left shifting. In fact, it's only simpler than left shifting because they're all ones. So first off, here's a,
write a 1, and then you go to the end and delete a 1.
yeah. So you replace the hash with a 1, the comma with the 1, and then you go to the end and you remove a 1. Now, of course, there's many correct ways to do this, and those designs would actually be better if when you're trying to do, convince yourself you could solve such a problem in binary. It may take a couple states, but you could definitely do addition in binary on a Turing machine. So we could do read a 1, write a 1, move right until we see the hash, and then we're going to just write a 1, and then move right, and then we're going to keep moving right until we see a blank. And then we're going to write that blank back, and then we're going to move left, and then if we see a 1, we're going to write a blank and move, it doesn't matter. Let me double check that. That sounds right though, right? Yeah. Notice in the design of the machine, each state is analogous to something. Each state is analogous to like a line of code, right? This is how you're going to design Turing machines. You're going to break them up into subroutines. Each one you're going to program with the very limited programming environment you're in, and then you're going to figure out a way to combine them in some way, right?
So in a sense, it's just a bunch of while loops and if loops.
Basically. But in conditions that you stop such loops upon reading the tape in some way, right? It's a very limited programming environment, but it's also surprising how powerful it is. So first off, how would you compare such an automaton to a PDA? It's not easy, but you could definitely pretend that tape is a stack. Unfortunately, the PDA is non-deterministic, so there's a small problem there eventually. We'll rigorously understand the power. Let's give some final quick definitions. So there's a few things. First off, we can say a function is computable if there's a Turing machine that halts on all inputs to compute the function. A Turing machine that halts on a partial number of inputs, we don't really consider an algorithm. But we need two words then, because we now have the possibility that on some inputs a machine could get stuck in a loop, and on some inputs it could be correct. So we say the class of language is LTM, such that L is an LTM if there exists a Turing machine, M, such that W is an L, if and only if M on W halts and accepts. And W is not an L, if and only if M on W halts and rejects. So these are the decidable languages. We say a language is Turing decidable or decidable if there exists a Turing machine that halts on all inputs to decide it. And again, this is in the decision model. Now we use the computable function model to do some interesting programming, but when we want to contrast this with other automaton, with PDAs, DFAs, and so on, we'll have to have a class of languages. So that'll necessarily be a yes/no question, so we use the decidable languages, right? But we have another definition because Turing machines are allowed to loop. So we say that L is an element of L star TM, and these are called recognizable. These are also called semi-decidable. These are also called recursively enumerable. These are the worst named object in history because they have several names that are all different. Such that if there exists a TM, a Turing machine, M, such that, well, if the answer is supposed to be yes, then M on input W halts and accepts. But if W is not an L, then M on W halts and rejects, or is stuck in a loop. So that's the difference between when a language is decidable and when a language is recognizable. A language is recognizable if there is a recognizer for it. By the way, every Turing machine, correctly programmed or incorrectly programmed, is a recognizer because it accepts some inputs, rejects some inputs, and gets stuck in a loop on some inputs, right? So every machine must recognize some recognizable language. Fine. What is the relationship between the decidable languages and the recognizable languages? Just given the definition.
Decidable is a subset of recognizable.
Every decidable language is recognizable. Just by definition, right? If it rejects or loops. So yeah. But it turns out that we don't really like machines that get stuck in a loop. So the definition of algorithm we'll use is going to be much better on the decidable languages. That's going to be the one that we care about the most. So, answering this question, whether or not these two are equal, is going to be the next focus of the unit. It's going to be the next major. Take us like 7 lectures or something to figure this out. So, any questions on these definitions? When a language is decidable versus when one is recognizable? All right.